They say we're currently living in revolutionary times. Specifically, we're now experiencing the fourth industrial revolution. The first revolution started in the 18th century and entailed mechanization of the industry. Key developments included the massive use of coal, the invention of the steam engine, and the expanded role of railroads. The second revolution, which started in the 19th century and went on until the beginning of the 20th century, was related to new sources of energy. That is, the utilization of electricity, oil, and gas. Improved communication via telegraphs, telephones, and later automobiles defined this era. The third revolution, which began in the 1960s, is associated with the expansion, or should I say ubiquity, of electronics, telecommunications, and computers. Nanotechnology, biotechnology, and robotics. And now, since the beginning of this millennium, we find ourselves in the fourth industrial revolution, also known as Industry 4.0. Enormous amounts of data, the internet, cloud computing, artificial intelligence, these are all terms you hear in the same sentence as Industry 4.0. And here's the deal. Companies need employees who are data savvy. Even if you were born almost after the revolution started, because it's been a couple of decades in the making, just because you grew up on YouTube or with an iPad in your hand, unfortunately, that doesn't make you data or tech savvy. Research shows that newer generations have been spoon-fed technology to the point of being unable to handle the underlying mechanics. When everything is point and click, or even within reach of one touch on a screen, you risk missing an opportunity to learn what's really going on. I'm talking about code. And I'm talking about mathematics and statistical savvy. We live in a world of storytelling and anecdotes, of fake news. I challenge you, the university challenges you, to bring data to the table before you make claims, before you speak. And data is not somebody else's anecdote or story. Data are reliable inputs whose source you understand and have insight into. Why should you write a thesis using quantitative methods? Because data is what you'll encounter in the future, and I encourage you to take the opportunity to experiment with data analysis. Data can be numbers, but it doesn't have to be. It can also be text. With the use of computers, even text can be analyzed in greater volume. Of course, the data, or text in this case, needs to be turned into something analyzable, and for statistical analysis, something quantifiable. By the way, I'm not talking about big data here. I'm just telling you to try out small data analysis, if you haven't done so already. Of course, your research question has to determine what method you choose. But start thinking about questions that would benefit from larger amounts of data. The most common question asked in accounting is there an association between this and that? But descriptive studies are also fine. Descriptive studies seek to answer the question, what does it look like? Unfortunately, too many qualitative studies are actually poorly conducted quantitative studies. What do I mean by this? The researcher or student of such a study asks the question, what does it look like? For example, what does it look like in company A, B, and C? And then an attempt is made to draw a conclusion, even while admitting that the results are not generalizable. If they're not generalizable, that is, if one has not been able to statistically determine the likelihood that the results are non-random, what's the point? One has to be careful about the type of question asked. If the question is, what does it look like? A desire to generalize is implied. If the question is, how can we understand phenomenon X? Then that's different. The purpose is not to generalize per se, in that case. There are good questions for qualitative analysis. But make sure you have identified one. You don't want to ask a question that requires a quantitative approach. Now, quantitative data-driven studies do have disadvantages, of course. The principle of GIGO applies, garbage in, garbage out. The data has to be reliable, and the models applied have to be appropriate. Otherwise, you may think you're looking at a lion when in reality you're looking at a domestic cat. A warning, don't go fishing. If you run enough tests, even the most improbable result is going to show up eventually. If you can assert something with 99% probability, if you run 100 tests, one of those will surely come out different. The most likely scenario is that you're going to want to study the association between some variables to see if they covary. Based on some theory, you predict that some factor x affects another factor y. Statistical tests, by the way, can never prove causality. However, your theory will have you predicting causality. There's nothing wrong with that. Ideally, you are able to conduct a random experiment. This is common in medicine and implies that you, for example, take your sample of 100 rats and randomly give a number of them, say half, a treatment. It may be a medicine, a virus, a certain diet, whatever. The other half doesn't receive a treatment. Those individuals constitute the control group. If the treatment group and the control group have a significantly different outcome y, probably their health or behavior in this example, the treatment x had an effect. X affected or caused y. Because the assignment of the treatment was random, we don't have to worry about other factors confounding the results. In the real world, it's unfortunately not that neat. In accounting, we rarely have access to random experiments. Instead, we study associations and infer causality. To do that, we need to control for confounding factors. We need to control for anything that might have caused y when we think it's actually x causing y. We sometimes call control variables z variables. A z variable is something that is associated with x and y, and whose effect on y may be incorrectly attributed to x. Let's take an example. Assume a theory that eating breakfast increases students' performance. We might have a testable hypothesis then that is, students who eat breakfast every morning obtain higher results on their exams than students who do not have breakfast. Assume we see an association between breakfast intake and exam results. Can we then conclude that eating breakfast boosts performance? First of all, exam results seem like a reasonable operationalization or proxy for performance. Thus, the variables used seem to be valid. Second of all, we can rule out reverse causality in this case. That is, it's not that exam results affect breakfast intake. That would be ludicrous. But what if it's something else that determines exam results that simultaneously affects breakfast habits? That is, while we want to draw the conclusion that breakfast intake makes students perform better, it could be that high-achieving students eat breakfast. That's the alternative explanation. One reason this might be the case is that exams are given in the morning, between 8 and 12. Because morning people are not only more likely to have breakfast than night owls, but also are more likely to be fully awake during the exam, it might simply be that we're capturing how alert someone is, or whether they're morning people or night owls. A test that controls for this fact is therefore necessary. In this example, one may perhaps ask students if they classify themselves as morning people or night owls and construct a variable based on that information. There are generally two broad types of variables when it comes to measurement: categorical variables and continuous variables. We can take the categorical variables and further divide them into nominal and ordinal variables. Nominal comes from name. These have data points that have no natural order. There are binary variables. They have two categories. For instance, breakfast intake or no breakfast intake in our example. And then there are variables with more than two categories. For example, did you have a large breakfast, a small breakfast, or no breakfast? When it comes to ordinal variables, ordinal comes from order. Data points on these types of variables have a natural order. This means that variables have an inherent rank. For example, in the case of exam results, A is better or higher than F. Then we have continuous or interval variables. An example is age. It has infinitely many decimals. Often, continuous variables are expressed as discrete variables without decimals. For example, your age is typically given as a discrete number such as 23, not 23.3587. You'd probably find someone who gives that as an answer to the question, how old are you? Pretty weird. Some variables are naturally discrete. For example, exam results, where you might have 30 points, 21 points, 43 points. The measurement level may influence the type of statistical test that is appropriate, which is why it's important to understand this concept. As for the structure of the data, there's cross-sectional panel and time series data. Cross-sectional data implies that you have an observation from each individual, one observation from each individual, such as exam results for individual 1, exam results for individual 2, etc. Panel data means you have several observations from each individual, such as exam results in January, March, and June for individual 1, and exam results in January, March, and June for individual 2. Time series data implies that you have several observations from a single individual, or of one phenomenon. This is most commonly used or observed in corporate finance, for example, share prices over time for a given firm. We do significance tests to answer the underlying question, what is the probability that the observed association is measured by chance alone? For example, the association may be assured at a 95% confidence level. But why do we do this? If we don't carry out a comprehensive study of the whole population, we use our hopefully random sample to draw conclusions about the whole population. We say that we make inferences about the population. Some selection errors are inevitable, however, which is why we test for the effect of chance in our sample. Normally, significant means that something is important. In statistics, significant means that something is probably true, and thus not caused by chance. Remember that research results can show that something is true without pointing that it is significant or important. Sometimes, therefore, people talk specifically about economic significance in economic research to emphasize the importance of the results. In all tests, there is an implied or sometimes explicit null hypothesis. For example, that the mean value of two samples or groups do not differ. In our student performance example, this translates to a null hypothesis. Breakfast eaters' exam results are on average not significantly higher than non-breakfast eaters. Or there is no linear relationship between two variables. In our student performance example, we have a null hypothesis. More study time does not give better exam results. Back to confidence levels and probabilities. You may have heard of 95% or 99% confidence levels. A 95% confidence level really means that there is a 5% chance of being wrong. That is, in the examples above, there's a 5% chance of saying that there is no association when there is none. You reject the null hypothesis when it is true. This constitutes a type 1 error. Then why not choose a confidence level of 99% or even 100%? The advantage is that the chance decreases from 5 to 1% that you make a type 1 error if you pick a confidence level of 99%. But the disadvantage is that the chance increases that you fail to detect associations that are there. In technical terms, you do not reject the null hypothesis when it is not true. Type 2 error is what that is. As type 2 errors are considered less serious than type 1 errors, the highest reasonable confidence level, given sample size and the expected strength of the association, is often chosen. So, following from the above, the more sure we want to be of anything, the higher confidence level we aim for. And the larger our sample should be. This is always going to be the case, whatever we're testing. Having said that, if we have a small sample and still get results, then the association is probably quite strong. If we want to be really sure that what we observe is true, why make selections at all, you may ask? Why rely on statistical inference? Usually, because it's impossible to get all the data on all the individuals, not least in the time of big data. The cost, in time and money, is infinitely high for some types of data collection. In general, the answer is that we use samples because they suffice. Of course, sampling means that there will always be sampling errors, since the sample will not be equal to the population. When is this a problem? It's a problem when there are systematic errors or bias in the selection process, meaning the selection criteria are such that the selected sample differs systematically from the population. It's impossible to answer the question, what is a sufficiently large sample? It really depends on the strength of the association and the statistical confidence level you're aiming for. Use prior studies in your field as benchmarks. As a general rule, though, the sample size should increase with the population size and the number of strata or subgroups of individuals that exist. Conversely, if the underlying population you are drawing inferences about is small and homogeneous, a smaller sample will still likely capture a representative portion of the population.